as well. Now, to drill down on some of these, one of the things that's going to be important for a number of reasons is energy storage systems. We really don't have good ways to store energy. We've got batteries that are kind of okay for consumer electronics, but really not what we need in terms of transportation, and definitely not what we need in terms of larger scale grid applications. And if you want to expand renewable energy, storage would be a big enabler because that would allow you to deal with the intermittency in a straightforward way. You'd store the energy when it's produced and you'd release it when it was demanded, and if those didn't line up, it wouldn't be a problem. The challenges are energy density and power density, the charging time. You can't necessarily take a whole bunch of energy in a short time frame. And actually overall lifetime, one of the challenges with the lithium-ion batteries that's a problem, particularly for vehicle applications, is their capacity degrades over time. If you have a smartphone, if the battery capacity degrades over time, you don't care as long as it lasts 2 years because you're going to get a new smartphone anyway. Cars we like to last longer than 2 years, particularly if the battery costs 10,000 US dollars. So that degradation of performance over time is a big problem for both vehicle applications and stationary uses. Another thing that's important is developing the power electronics that allow you to switch around between all these things, and to do so in a reasonably efficient way. And also there's a bit of a software challenge in the sense of integrating all these things together. If you've got the storage capability and you've got all the switching that you need, this is a very complex system to manage. So it requires a certain amount of connected intelligence in order to make the whole thing work efficiently. That's probably the easiest part of the equation. I think the power electronics, we have pretty good options. The energy storage is not really where it needs. Right now, at grid scale, the best energy storage we have is to pump water up a hill, which works, but it only works if you have a hill, and it's got to be a hill that the people at the top of it, don't get upset when you flood them out. And there's a limited number of options for pumped hydro storage. It's very valuable energy, it turns out. So in terms of where is the biggest potential, it turns out it really is solar. So if you look, and I'm going to switch units, I apologize. I showed you the curve that showed how many quadrillion BTUs we would need by 2040, 2050. If you figure that out in terawatts, it's 15 terawatts. And it turns out that to get 15 terawatts is really not that hard. If you don't care about CO2 emissions, we'll get there. Through a combination of windmills, fossil plants, whatever, we can get to 15 terawatts probably, and some limited use of solar. Now, if you project forward and even if population is leveled off, you're still going to be growing standards of living. That starts to get to about 20 terawatts by 2100. At that point in time, if you do the inventory of hydroelectric, fossil supply, eventually now you're running into maybe uranium supply problems and so forth. Some of the fossils are going to be going down in terms of either availability or the allowability of use because of CO2 emissions. It starts to be more of a problem by 2100. You could have a shortfall of around 10 terawatts by then, unless you could take good advantage of this resource. The practical solar production capability with reasonable efficiency and actually not totally ridiculous land use is still enormous. If you get just the kind of efficiencies that we really have already, maybe you go from 10 to 20%, not totally crazy, and you look at the sort of land mass that is reasonable to imagine devoting to this, you're talking about 600 terawatts. A huge resource compared to any reasonable projection of what we need. So it's not fundamentally an energy supply problem in terms of the amount of energy that's incident on the Earth. Now, whether or not you can do this in a practical way and an affordable way, that's a very different question. And that's where you get into things like, do you have energy storage? Can you control the grid? What's the cost of solar and all that sort of thing? But in terms of just basic energy supply, solar by itself could take care of the whole problem. So what are the barriers to solar? The materials costs are relatively high. And by materials costs, it's not just, say, the materials cost of a photovoltaic cell. The price of PV has come down very fast because of the scale-up of production in China. And now, the cost of a solar panel, only 1/3 of that cost is the photovoltaic. The rest of it is the frame around it and the power electronics to connect it to the grid and the cost of getting a permit from your local electricity company and all that sort of stuff. So, you know, you've got to have low-cost materials, not just for the conversion, but also for the whole balance of the infrastructure. In terms of the, as I said, it's not just biofuels, but also biomaterials. That has to do with how you're going to convert effectively solar energy into chemical fuels, either through biological or chemical means. And this is not very attractive from a cost point of view with current technology. There are specific instances where you can kind of demonstrate it. You can do it at a laboratory scale, but not generally competitive with petroleum or even particularly close. So we need good catalysts in particular. There might be ways that you can reduce the cost by getting systems that actually self-assemble. That's sort of a little bit more. I said we got till 2100, so we got some time to do some difficult things. You need to worry about thermal management because actually with photovoltaics, their efficiency goes down as they get warmer. So you can't just focus onto them. You start to lose efficiency. So if you can thermally manage them, that would help. It'd be good to have transparent conductors. There may be clever ways. Again, this is sort of in the self-assembly mode. Self-assembly, we kind of tend to think about chemical-type processes, but there's also biological routes to self-assembly, things like nanofermentation. It turns out there are bacteria that if you put the right chemicals in, they basically poop out photovoltaic materials. Now, it's not really high-grade stuff. It was